intuitive. So today's going to be understanding a lot of vocabulary, to be honest, because the big thing about understanding vocabulary is if you don't, you just won't know what it's asking you. So if you know what it's asking you, it's pretty easy. So first of all, this is 6-1 Radian and Degree Measures. So how are angles formed, everybody? So, well, first of all, we obviously have to have some initial side. We have to start somewhere. So right here we have our initial side, and I open up to a terminal side, creating an angle. So if they ever say terminal side, that just means the stopping point of the angle. Everyone? Okay. So now another thing is angles in standard position. Right here I have an angle just floating in thin air. Right here is an angle in standard position. Standard position means instead of just drawing an angle floating in thin air, draw on an XY chart. Standard position puts it on an XY chart. So everybody right here would be 0. This is my initial side, and then I can create an angle. So I'm opening up to a terminal side here. Does everybody see how that angle is created in standard position? Yes or no? Okay, well then, if we have angles in standard position, that can create positive and negative angles. So positive angles open upwards first. Then they go around this way, which would be counterclockwise. That would create positive angles. Negative angles start by going down first. So that would be clockwise, creating negative angles. We have positive angles and negative angles. Now this is where I would write down maybe the first vocabulary word I would write down. Coterminal angles. We will use this the rest of this unit. This idea of coterminal angles. So coterminal angles land in the exact same spot as the angle. A coterminal angle will fall in the exact same spot. In other words, it'll have the same initial side and the same terminal side. Yeah, it's a different angle, but it falls in the exact same spot. So notice right here, I have an initial side of 0, and I've opened to a terminal side of 30 degrees. A coterminal angle would also have this initial side, and here's an example. If I went around all the way and ended up right there, do you see how I would have the same terminal side, everybody? How many degrees would that be? 390, wouldn't it? I went around a full, starting at 0, I went around a full 360, and then add 30 more. So right here, I would end up at 390 degrees. So 390 degrees and 30 degrees are coterminal angles. They fall in the exact same position. So now think about it. There are an infinite number of coterminal angles. Couldn't I add 360 again? Add 360 again. Add 360 again. Now couldn't I, if I wanted, have a negative coterminal angle? Here's my initial side. To end up in this same position right here, couldn't I go down and end up right there? So what did I technically do? Subtract 360. So to find coterminal angles, you can add 360 an infinite number of times, and you can subtract 360 an infinite number of times. And that'll put you in the same spot. We're subtracting though, to go backwards, right? Didn't I just create a negative angle? Oh, okay. So you do 30, so you'd start here, to end up back here, you'd subtract 360.
Oh, okay, I thought you were starting at the...
Sorry, my bad. Sorry, my bad. I probably said that weirdly. You're right. Alright, so, if I asked you on the homework, given 120 degrees, find a positive coterminal angle and negative coterminal angle. That just means it needs to fall in the same spot. This isn't in standard position, but we get the idea. 120 degrees would land in the same spot if I added 360 degrees. Do you agree? And if I took 120 degrees and I subtract 360 degrees, I will end up in the same spot. Are we all good with that? So there would be a positive and coterminal angle. So wouldn't that be 480? 480 is a positive coterminal angle, and then 120 minus 360. Okay, awesome. Negative 240 degrees would be a coterminal angle. Okay, awesome. Now look at this one. It starts out at negative 420 degrees. Negative 420 degrees. If I add 360, what degree measure am I at? You're right, negative 60 degrees, everybody. So wouldn't that be a negative coterminal angle? Yeah, it's negative. You guys see how that is a negative coterminal angle. So to get a positive coterminal angle, I actually have to add 360 again, which would put me at 300 degrees. So notice, because it was so small, when we added 360, it was still our negative coterminal angle. And then now we have a positive coterminal angle. Okay, awesome. I think we get the picture there. So go ahead and go to the homework and do just the odds, because that's what's assigned on the homework. I only care that you do the odds. So right now I would just do 39 and 41 off of the homework. It's asking you to find positive and negative coterminal angles. Before we move on, do those. That'll be really quick. Now we know that coterminal angles fall in the exact same position. What would complement and supplement angles look like? So complement angles have a sum of 90 degrees. The two angles will add up to be 90 degrees. That's what complementary means. Complementary angles add up to be 90 degrees. Supplementary angles add up to be 180 degrees. So two angles would add up to be 180. This is important. They have to be two positive angles. So you can't do subtraction. It has to be they add up to be 90 degrees. They add up to be 180. You can't subtract. So there are angles that don't have complements and don't have supplements. So let's just look. These are just the evens on the homework, but they're really straightforward, so you're not going to need to take notes. I mean, you probably want to write down this part. But for this part, you can probably just get a picture. So on 44A, it says find a complement and supplement of each angle if possible. So everybody, 3 degrees plus what equals 90 degrees? 87 degrees. Therefore, my complementary angle is 87 degrees. Pretty straightforward stuff. These two are complementary angles. Now supplement, the supplement would be 3 plus what equals 180? 177, right? That would be our supplementary angle. Okay, let's do 44B. So you would say 64 plus what equals 90? 26. So our complement is 26 degrees. And the supplement, 64 plus what equals 180? 116. Good. Now look right here though. 46A, 130 doesn't have a complement. No, because we have to subtract to get back to 90. So you can't do that. It has to be addition. There's no complement. Our supplement, however, is 50 degrees because that can go to 180. So same here. The complement, to get back to 90, would take subtraction. That doesn't work, so no complement. Our supplement would be 10 degrees. Okay. So let's just get those ones done off the homework as well. Just do the odds. So everybody listen, okay? So we're going to now be talking about the difference between a degree and a radian. It's actually really straightforward, everybody. So a degree is the measure of an angle. Like right here, here's my terminal side, and I've opened up to this angle theta. I'm not putting an angle on it. It could be 45 degrees, it could be 40 degrees, it could be 36 degrees. Do you guys see? That's just the measure of the angle. So this is a degree measure, the measure of the angle. Now what's the radian? Well, a radian is literally this. Everybody, listen to what a radian is. A radian is just the actual physical length of the arc that is created when opening up an angle. So do you see the length from here to here? The physical length of the arc is what is the radian. So we have an angle that opens up and it creates an arc with physical length. That's the radian part. That's it. So a radian is the length of the arc that the angle opens up on. So if I said to you 45 degrees, you could want to know, well, what's the length of the arc here? And that would be the radian measure, which we'll learn how to get there in a second. So now, this isn't actually hugely important. I just want to show you where 2 pi comes from. That's why the only reason I'm getting into what 1 radian is, okay? So 1 radian, like the physical length of 1 radian, is the measure of a central angle that intercepts an arc. So we have an angle that opens up and creates an arc. When we have a radius that is equal to length as the arc, that is by definition 1 radian. So let me say that again. Here is my starting point. I've just opened up an angle. Do you agree? Yes. Is it possible that this physical length of the radius is the same as this length? Look at it. That's teeny. Is the radius much longer than that? So that's not 1 radian yet. Do you guys see what I'm doing here? So I got to go further. Now, does this look like a reasonable amount to be the same length as this? This amount and this amount look pretty much the same length. Boom, there's 1 radian. Does that make sense? So from here to here, let's say once the radius, this length and this length are the same length, then that's 1 radian. So if I keep going, keep going, keep going, keep going, now would you say that that length is about the same length as the radius? Roughly? Now we've gone 2 radians in length. Do you guys see? So we just keep going. Now we've gone 3 radians in length, and so on. So that is what our 2 pi comes from. Physically, look right here. So here is 0, everybody. Here is 0. And I've now created 1 radian. I'm telling you that this length and this length are the same. Okay, everyone? So I created 1 radian, then 2 radians, 3 radians, 4 radians, 5 radians, 6 radians, and then don't we need to go just a little bit more to get back to 0?
Yeah.
Well, where does this just over 6 radians come from? Well, we know that the full circle is 360 degrees. Do you agree?
Yeah.
Which is 2 pi in physical length. That means the outer length of this circle is 2 pi in length. Now that doesn't give much meaning. Let me show you. Everybody type into your calculator. 2 times pi. 2 times pi. You get 6.3. So the distance around is 6.3-ish radians. Do you guys see? This is the degree measure. This is the pi radian, the pretty answer. This is the decimal radian. Radian, radian. This is how an engineer would want it, because that's very tangible. 6.3 inches. Is that better than 2 pi inches? For an engineer, yes. Do you guys see what I'm saying? A mathematician would want this radian. An engineer would want this radian. So it's the same thing, though. So now what happens when we start changing the radius of our circle? Because not all circles are the same length. All we have to do is take that physical length of 2 pi and times in our radius. And boom, there's the physical length of that new outside of the circle. That's why circumference is 2 pi r. What does circumference mean? The outside distance of the circle. Does everybody know that? Didn't we just talk about how the outside distance of a full circle is 2 pi in length? But now what happens when I change the radius? That changes the physical length. So then you just times in the radius. So if I have a radius of 5, what would be my physical length of my circle? Radius 5.
31.5. No, 41.
So that would be 10 pi.
Yeah.
And then you times it and you got about 30.
31.4 inches.
Cool. So now do you guys see? This would be the math answer. This would be the decimal answer. Any questions on that? A degree versus a pi radian versus a decimal radian. Yeah? Okay, awesome. I remember that used to really confuse me. I'd be like, well, what's the difference between 6.3 and 2.2 pi? They're the same thing. Just pi's been multiplied in the decimal radian. Okay, awesome. Now, if you see the word revolution, 1 full revolution means 2 pi, going around a circle once. So if it says a circle has gone 1 full revolution, you would say it's gone around a full circle of 2 pi in length. Okay, so then this is just kind of the basics. We're not getting into the unit circle today, but this is where the unit circle comes from. If we have a full revolution of 2 pi, that means a full circle of 2 pi, can't I cut it up into different sections here? Well, if I cut up this 2 pi in half, taking 2 pi and dividing it by 2 or timesing it by a half, won't I get pi?
Yeah.
That's why this physical distance from here to here is pi in length. And then if I take the 2 pi and cut it into fourths, so I can have these quadrants, wouldn't that be pi halves?
Yeah.
Pi halves, do you guys see? So this is 1 pi halves in length. Look, 1 pi halves. So if I'm going another pi halves, how many pi halves would that be? 2 pi halves, which is pi, right? This must be 3 pi halves, and this must be 4 pi halves, which is 2 pi. Do you guys see how it's all working out? Okay, awesome.
I remember this one.
Yeah, so we can cut it up however we want. Right here I've cut it up into a 6. So here's 1 pi thirds, then 2 pi thirds. Where would 3 pi thirds fall? Right there, 3 pi thirds. Don't we know that's pi? So then wouldn't 4 pi thirds be down here? Do you guys see how that kind of works? Okay, awesome. All right, so we'll get into the unit circle more later, but I just wanted to show you how that's used. All right, so now we know we have quadrant 1, 2, 3, and 4. If I say to you, what quadrant does an angle fall in, you can answer me. So if I said to you, what angle, I said that really weird. Which quadrant does angle 190 degrees fall in? What would you say?
3.
3, going around positive 190 degrees would put me in quadrant 3. So that's what's it's gonna ask us, which quadrant does your angle fall in? So let's look at some examples from the homework. This is 36. So what it says is sketch the angle in standard position. This is what you would do. You would draw an XY chart. I want to see an XY chart like that, okay? So we're drawing in negative 270 degrees. There's two ways to do it. You first of all have to draw your initial side, correct? Now, I need to go negative 270 degrees. So doesn't that mean I need to be going down? Now, which quadrant will that fall in? So, yeah, you're right. Here's positive 270, correct? So going up 1, 2, 3, you guys see? If I go backwards, 1, 2, 3, that would end right here, wouldn't it? Right there is my terminal side. Here's my initial side. Here's my terminal side. Now, the only thing we have to draw in is and we went backwards because it was a negative 270. That's how you would draw the angle. Pretty straightforward stuff. Now, another way to see, like if you don't like drawing negative angles, like I personally would always rather draw a positive angle, so I would find the coterminal angle, because won't it fall in the same spot? Yeah. So I add 360 and I get 90 degrees. To me, it's easier to go, okay, well, initial side 90 degrees is here, and there's the same angle, isn't it? It falls in the same spot. But then I would say, but I'm not drawing 90, so I'm not going to point this way. I've got to point backwards, because that was negative 270. Does that kind of make sense? Okay, let's draw negative 120. So this is what you do on your homework and on the test. You go XY chart. We have an initial side here, and then negative 120. Which quadrant? Let's see.
No, quadrant 2, wouldn't it?
So we're going down, right? So it's right here somewhere? So you would draw like that. Rough sketch, it doesn't need to be perfect. Now once again, you could take negative 120, add 360, and you get 240. If it's easier for you to draw 240, that's fine. You guys see how 240 was between 180 and 270-ish? So that would be here, and then just draw it backwards. Okay. Determine the quadrant which each angle lies. If I don't want to have to go negative 260, can't I just find the coterminal angle? Negative 260 plus 360 is 100 degrees. So which quadrant? 2. Perfect. Negative 3.4 degrees is super easy. What is that? 4. Quadrant 4. Pretty easy. Okay. Okay, this says find a positive and negative coterminal angle. So if they gave you this picture and said given this angle, find a positive and negative coterminal angle, we're just going to use our hands and do some algebra. It's going to be way easy. So isn't it true to find a positive coterminal angle, we add 360 degrees? Yeah. Well, this is a radian, so we're going to add 2 pi, because that is the same thing as 360, but as a radian. Then we're also going to take 7 pi 6, and we're going to subtract 2 pi. And now we have to do some math. You could do it by hand, or you could do it in your calculator, but everybody listen, if you do it in your calculator, you cannot type pi in. Did you all hear that? If you ever type pi in, your calculator cannot put it back in a fraction. So let's say you didn't want to do it by hand. You would go parentheses, 7, 6. Notice I did not type in pi. Did you notice? 7, 6 plus 2. Math, enter, enter. 19, 6. So I got 19 pi 6. Does that make sense? I always have people say, Ms. Christensen, it won't convert. And I say, don't type pi in. They're like, oh yeah. So what would I type in here if I wanted to not do it by hand? 7, 6 minus 2, and then I'd hit math, enter, enter. And that's negative 5, 6. So I'd say negative 5 pi 6. There's a positive and a negative coterminal angle. Okay, write this down. We need to be able to convert back and forth from degrees to radians and radians to degrees. There are times when it would be better to have a degree measure, and there are times when it would be better to have a radian measure. In story problems, we're going to want radian measures. In graphing, I always like to graph something in degrees rather than radians, so it's just good to be able to switch back and forth. So if we start with a degree to get to a radian, you're going to multiply by pi radians. You don't need to write the radian part. Pi over 180. Now notice pi and 180 are the same thing. That is like timesing by a fancy 1. Pi over 180 is just a 1. Now, why would I put the degrees on bottom? Because don't we want degrees to divide out? So it always helps to know that, because then you remember which one goes on bottom. So if you start with a radian and you need to switch it to a degree, you're going to do by the reciprocal of that 180 over pi. Now, once again, we need our radians to divide out, so it makes sense that if there's radians on top, there needs to be radians on bottom. And then we'll just have switch back and forth. So let's just do these quick examples here. So you would literally, everyone, grab your calculator. I just want to make sure we all understand how to use it correctly. Convert from degrees to radians. So you'd say I'm going to times this by pi over 180 degrees. Once again, degrees go on bottom because I need my degrees to divide out. Now, yes, I have full confidence you could simplify that fraction by hand, but you could also just go 135 divided by 180. Don't type pi in. Math, enter, enter. You get 3/4. So the final answer would be 3 pi fourths. Does everybody agree? So we times by pi over 180. So then you do negative 270 divided by 180. Math, enter, enter. And you get negative 3 halves. So that'd be negative 3 pi halves. So you can just use your calculator to be efficient and quick. Let's go the other way. Starting with a radian, go to degrees. So this time we times by 180 over pi. I want to make a point here. Isn't it true that by hand I can divide out my pi's? Yeah. So now I'd have negative 180 divided by 2. Negative 90 degrees. True. Okay, right here we times by 180 over pi. And look again, my pi's can divide out by hand on this one. So you do 9 times 180 divided by 2. I got 810. 9 times 180 divided by 2. I bet you just hit something wrong on that side. Now this is where people freeze up. Everybody listen, I remember this is where I used to freeze up in high school. They'd say, convert this to degrees. And they go, well, there's no pi, so what do I do? Yes, there sure is. There is a pi. It's just, it's already been multiplied in. Do you guys see how here it was not multiplied in? They left the pi out. Isn't 9 pi halves the same thing as 9 times pi divided by 2? 14.1. Do you guys see how they're no different? The pi has already been calculated in, so it's still the same thing. You're going to times by 180 over pi. Now, up here, the pi's could divide out by hand, but the pi is multiplied in, so you can't divide it out by hand. Do you guys see? So you would have to type it into your calculator. Just do 2 times 180, hit enter, divided by, and then you have to do pi in your calculator. Do you see the difference? So that's 114.59 degrees. So don't let pi radians versus just radians mess you up. There's still a pi in there, it's just been calculated in. Okay, yeah. Awesome. Okay, do some of those on the homework for a second. Learned, okay, everyone, do you listen to this? We just learned if we have an angle of 45 degrees and we open up right here, can't I find the physical length of the arc? Wouldn't that just be the radian? So you would take and say, well, what is that? Well, to go from 45 degrees to radians, we just learned to times by pi over 180. Does everybody agree? So wouldn't that be pi? Yes, pi fourths, everybody. So this length from here to here is physically pi fourths. Now, once again, that's a math answer, a mathematician answer. An engineer would say pi divided by 4. So they'd say it's 0.78 inches or whatever. 0.78. You guys see what I'm saying? So, well, that makes complete sense. But look at this smaller circle. If this is 45 degrees, what's the length of this arc? Pi fourths, right? So that is 0.78. Well, that's a problem. This is a bigger circle than this circle. They can't both be 0.7 in length, 0.78 in length, right? So what are we missing here? The radius. So all we have to do is say, yeah, it's 0.78 in length, but now we got to times in our radius. So now times in by 10, times by 5, and boom, there's the actual physical length. Does everybody see? So that's why this is the formula. The length of an arc is going to be your radius times by your theta times by your angle. However, because we're dealing with length, your angle has to be in radians. So that should be a really easy formula to remember. Radius times theta. And hopefully it makes sense of why that is. What is that? S is the length of the arc. So now we would do, so once again, now you could say this is 7.8 inches, where this 0.78 times 5 was 3.9 inches. Do you guys see that? Just the radius is what gives us the difference there. Okay. So let's read this problem here. It says a circle has a radius of 4 inches. So I draw a circle. I have a radius of 4 inches. And it says find the length of an arc that is intercepted by a central angle of 240 degrees. So if I create 240 degrees here, it wants to know the physical length of the arc from here to here. So the S is equal to radius times theta. The length of our arc is equal to our radius, which is 4, and our theta, which is 240. Now if you give me an answer in degrees, and think about it, that wouldn't make sense. I'm asking you for the length of an arc. If you say 4 times 240, there's 960 degrees worth of arc. That's not a length. Do you guys see what I'm saying? So now how do we convert that? Times by pi over 180, and then we wouldn't type in the pi part, so just do 960 divided by 180. Yes, and then hit math, enter, enter. I want the simplified fraction. So S is equal to 16 pi thirds. This is the mathematician answer, but once again, if you went to an engineer and said, you have 16 pi thirds inches worth of whatever, they'd say, just tell me how many inches, dang it. So you'd say, you would do 16 times pi divided by 3, so that's 16.75 inches worth of arc. I want to see a math answer and an engineer answer. Is this making sense to everybody? Okay, cool. Okay, last formula you need to know is the area of a sector. Area of a sector literally just means exactly what it says. Area of a section of a circle. A sector just means section. So instead of finding the area of a full circle, we only want to be able to find the area of just a small section of the circle. So now look at the formula and how it's derived, because it's a lot easier to remember if you understand where the formula comes from. So look, area of a full circle is pi r squared. We've known that for a long time now. Area of a circle is pi r squared. Do you agree? But now, if we only want this theta, if we only want this section out of the full section, and then find the area, look at the formula. Take that theta, that section, out of 360, and then find the area of that. Do you guys see? Yeah, theta out of 360. I want this out of 360's area. Yeah. Now, this would need to be typed in degrees. So look, I've just rewritten that same formula. This formula would need to be typed in degrees, so theta would need to be in degrees. If it's in radians, you have two options. Convert it to degrees, then plug it in, or use this formula. If you're given the theta in radians, then you would need to use this formula. So just because, look, the radian would divide out, 360 is 2 times 180. Isn't 180 and pi the same thing? Then these divide out, so then now we have this formula if you're doing it in radians. We're going to mostly be given it in degrees, but just so you know. Just really you need this formula right here, that's it. I personally only know this formula, so if I'm ever given the angle measurement in radians, I usually just convert it back to degrees and then plug it in. So look how easy this is. Last example of the day. A sprinkler on a golf course is set to spray water over a distance of 70 feet. It rotates through an angle of 120 degrees. Find how much grass will be watered. Now look, that literally is a real, true, real life story problem. Think about a sprinkler. What happens is it shoots out an amount of water, and then those sprinklers work like this. Agreed?
Yeah.
That's what sprinklers do.
One area of grass and it always dies and you're annoyed.
Yes, exactly. It misses an area. So look, we're just finding the area of that section of a circle. So you'd say 120 out of 360, then pi on our radius squared. So pi times 70 squared. Now I need everyone to listen carefully. To find the math answer, the mathematician answer, not the engineer answer, you cannot type the pi part in. So what you can do is do 120 times 70 squared. Order doesn't matter. Doesn't times and division all work the same? 120 times 70 squared, I hit enter, divide by 360. I get a decimal. I need to hit math, enter, enter. So that would be the simplified fraction of all this stuff is 4,900, and then it was over 3, so pi thirds. Does everybody see? And you'd say, feet. That's how much feet it covers. But if you went to Farmer John and said, Farmer John, I've done your calculations, 4,900 pi thirds feet. He'd say, well, what does that mean? And you would say, well, I'll tell you. You'd say, okay, 5,131.3 square feet. And Farmer John say, that's more like it. Okay. All right, that's the end. So do the homework. It's on your paper.